In April 2025, astronomers detected something truly unusual. A mysterious signal had traveled 124 light-years across the vast emptiness of space, originating from a distant exoplanet known as K2-18b. But this wasn't just noise. This time, the chemical signature was stronger, clearer, and, most importantly, stranger than anything we've ever seen. Some researchers were so excited, they went straight to the headlines. We might have found alien life. Others raised eyebrows. Was this truly a sign of extraterrestrial biology? Or was humanity once again misinterpreting the cosmos through our all-too-earthly lens? What exactly is K2-18b? And what kind of secrets does this deep ocean world hide beneath its pink hydrogen skies? Strap in, because we're about to travel 124 light-years into the unknown, to a place that could rewrite everything we know about life, the universe, and our place within it. There are hundreds of billions of planets in the universe. So why did this one, this oddly named K2-18b, become the scientific community's obsession overnight? To answer that, we have to rewind to 2015. The Kepler Space Telescope, one of NASA's most successful planet hunters, was scanning a patch of sky near the constellation Leo. Its mission? Detect tiny dips in starlight that might reveal hidden planets. And there it was, a planet orbiting a dim little red dwarf star. At first glance, K2-18b didn't seem like a big deal. Red dwarfs are everywhere, and planets that orbit them usually get tossed into a massive database, labeled, logged, and largely ignored. But then came the second look. This planet didn't act the way it was supposed to. It wasn't solid and rocky like Earth, nor was it a giant gaseous swirl like Neptune. It was something in between, something strange, new, and difficult to define. Scientists eventually gave it a name that sounded more like a sci-fi experiment than a planet. A Hycean world, short for hydrogen ocean. This new planetary classification described something Earth had never seen. A planet covered in deep, global oceans, with no land anywhere. An alien water world, blanketed not by blue skies, but by thick, pink clouds of hydrogen gas. Imagine standing on that world's surface, if there even is one. There are no continents. No beaches, no mountains, just water stretching endlessly in every direction and above you. A permanent dusk under layers of rose-colored clouds, like standing in an eternal sunset. It's beautiful, it's surreal, and it's deeply unsettling. Because unlike Earth's relatively shallow oceans, the oceans on K2-18b might be hundreds of kilometers deep. That's far beyond anything life on Earth has ever known. And yet, here's the truly wild part. Despite orbiting a faint red star and completing a year in just 33 Earth days, this planet might still be warm enough to support liquid water. Why? Because K2-18b is wrapped in a massive hydrogen atmosphere, a planetary thermal blanket that traps heat like an industrial-grade greenhouse. So even though its star isn't bright, the surface may still be temperate enough for oceans, maybe even for biology. In 2019, the Hubble Space Telescope made a shocking discovery: water vapor in the planet's atmosphere. That alone made headlines. For the first time ever, humanity had detected water on a planet located in the so-called habitable zone, the Goldilocks region where temperatures might allow liquid water to exist. It was a tantalizing clue, but it wasn't until 2023 that K2-18b truly exploded into the global spotlight. That year, NASA's James Webb Space Telescope, the most powerful observatory ever built, turned its golden eyes toward this strange ocean world. The data it returned was more precise, more detailed, and more baffling than anyone expected. Webb confirmed the presence of water vapor. It also detected methane and carbon dioxide, both molecules that, on Earth, are closely tied to biological processes. But there was something else. A bizarre, hard-to-explain trace gas. One that sent half the scientific community into a frenzy. Its name? Dimethyl sulfide, or DMS. And here's why that matters. On Earth, DMS is almost exclusively produced by living organisms, especially microscopic marine life in our oceans. Let that sink in for a second. A chemical that's almost always associated with life, now potentially detected in the atmosphere of a planet 124 light-years away. Naturally, scientists began debating furiously. Was this proof of alien biology, or just an elaborate cosmic coincidence? If you're fascinated by alien oceans, strange atmospheres, and the search for life beyond Earth, go ahead and hit that subscribe button. This channel dives deeper into the cosmos than you've ever gone before, and trust me, you won't want to miss what's coming next. When scientists coined the term Hycean world, it wasn't just for K2-18b. It was the birth of a new class of exoplanets, ones that don't fit neatly into our traditional models. In some ways, these are the misfits of the universe. Too big to be Earth-like, too small to be gas giants, and with atmospheres that break all the rules. But Hycean worlds might just be the best places to look for alien life. A Hycean planet is typically 2 to 3 times the size of Earth, with masses up to 10 times greater. They're believed to have rocky or icy cores, but their defining feature is a thick hydrogen-dominated atmosphere and vast liquid water oceans. Why hydrogen? Because in the early days of planetary formation, hydrogen is the most abundant element in the universe. Planets that formed quickly and didn't lose this light gas may still have massive hydrogen envelopes today. On Earth, hydrogen doesn't stick around. It's too light, and our gravity isn't strong enough to hold on to it for long. But on a bigger world like K2-18b, that's not a problem. The result? An atmospheric pressure and chemical environment utterly unlike anything on our planet. And here's the kicker. Under the right conditions, hydrogen atmospheres can retain heat extremely efficiently. This means that even if a Hycean planet orbits a cool, dim red dwarf, it might still have liquid water on its surface. Water, heat, atmosphere. That's 3 critical ingredients for life as we know it. But let's get one thing straight. Hycean worlds aren't Earth 2.0. They're not paradises with green trees and blue skies. If anything, they're more like Lovecraftian ocean worlds, wrapped in thick clouds, boiling with chemistry, and hiding whatever secrets may lurk deep in their alien seas. And yet, they might be more habitable than we ever imagined. This is where the real magic and science happens. Because when we say we detected water vapor or spotted DMS on K2-18b, we're not talking about seeing clouds or ocean waves through a telescope. That kind of resolution is still decades away. Instead, we're reading the chemical fingerprints of light. It works like this. As a planet passes in front of its star, what astronomers call a transit, a tiny fraction of the star's light filters through the planet's atmosphere. Different gases absorb different wavelengths of light. By analyzing the spectrum of that light, we can figure out what molecules are present. It's not easy. The signals are incredibly faint, and they have to travel across unimaginable distances. The process requires precision instrumentation, massive computing power, and mathematical modeling to even get a hint of what's floating in an alien sky. The James Webb Space Telescope was designed for this kind of work. With its infrared vision and unprecedented sensitivity, it can detect trace gases in distant atmospheres with far more accuracy than anything that came before it. And what it saw on K2-18b blew the doors wide open. Webb's observations revealed a surprisingly rich atmosphere. Among the chemicals detected, water vapor, H2O essential for life. Check. Methane, CH4 on Earth, both biological and geological. Carbon dioxide, CO2 same story. Volcanoes make it, but so do organisms. Dimethyl sulfide, DMS wait, what? Now, DMS is the wild card. On Earth, 95% of atmospheric DMS comes from marine phytoplankton, microscopic life floating in our oceans. They release it as part of their metabolic processes. DMS has a slightly fishy, cabbage-like smell. In fact, if you've ever stood near the coast and caught a whiff of that ocean breeze, you were probably smelling DMS. So you can imagine the excitement when scientists detected even a hint of it on a planet covered in alien oceans. It was the closest thing we've ever seen to a biosignature, a chemical marker that screams, something is alive here. But that's when the real debate began. Some scientists were ready to pop champagne. This is it. This could be the discovery of the century. Others were quick to throw cold water on the hype. It's too early. The signal is too weak. This could just be noise. Who's right? Let's explore both sides. Proponents argue that DMS is a short-lived molecule. It doesn't last long in an atmosphere. For it to show up consistently in Webb's data, there must be a stable, continuous source, something producing it on a regular basis. What else could do that besides biology? There's also the planetary context. K2-18b has oceans, moderate temperatures, and the right pressure for complex chemistry. If any world were to support some form of oceanic microbial life, it might be this one. They argue that we're not just detecting one compound. We're seeing a chemical system that mirrors early Earth. That's not proof, but it's a damn good clue. But not everyone is convinced. First, They point out that DMS can be produced abiotically, without life. Some rare chemical reactions, especially involving sulfur and carbon compounds, can mimic biological outputs. In fact, in 2024, the Rosetta spacecraft detected DMS on a comet, 67P/Churyumov-Gerasimenko. No life there, just ice and rocks. Second, the signal is extremely weak. It's barely above the noise threshold. Webb is powerful, but even it can be fooled by instrument interference, stellar contamination, or statistical anomalies. In short, this could all be a giant cosmic false positive. Are we projecting our own biology onto the universe? We're so used to life as it exists on Earth, oxygen-breathing, carbon-based, sunlight-powered, that we often assume alien life must follow the same rules. But K2-18b is nothing like Earth. Its oceans are deeper. Its air is hydrogen-rich. Its sun is colder and redder. The surface, if it has one, is likely shrouded in pressure and chemistry we barely understand. So the real question is, are we even capable of recognizing life that isn't like us? Could life exist that doesn't produce familiar gases, or that thrives in environments we consider hostile? If so, then relying on DMS, or any single chemical, as a marker for life might be like looking for a heartbeat in a jellyfish. K2-18b is likely covered in an endless ocean, thousands of kilometers deep. There are no continents, no mountains, no beaches, just water, stretching horizon to horizon under a sky the color of wine. And this ocean isn't calm. With high gravity, dense hydrogen air, and likely strong tidal forces from its red dwarf sun, the waves could tower, the currents could twist with strange physics, and the depths might press with unbearable weight. But where there's water, there's potential. On Earth, life emerged in the oceans. Not on land, not in the sky, but in the dark, crushing pressure of Earth's ancient seas. Maybe on K2-18b, life never needed to leave the water. Here's where things get weird. K2-18b might not even have a solid surface in the traditional sense. The transition from ocean to core could be gradual, water slowly becoming supercritical fluid under pressure, then eventually merging into exotic ices or rock. So any life would likely live in the upper layers of the ocean, where light, energy, and chemistry interact. On Earth, we call this the photic zone, a few hundred meters of sunlit water where plankton bloom, fish swim, and ecosystems thrive. K2-18b might have its own version of this. But instead of sunlight filtering through air, it would scatter through hydrogen clouds, glowing in infrared hues from a dim red star. Could something evolve to capture energy from a red dwarf sun? Absolutely. In fact, some Earth microbes already thrive on infrared light. Deep under the ocean, where visible light can't reach, certain bacteria use infrared chemosynthesis near hydrothermal vents. On K2-18b, the dominant wavelengths from the star K2-18 are in the infrared and near-infrared bands. So if life exists, it's likely tuned to those frequencies. Instead of green chlorophyll, alien organisms might use black, purple, or even metallic pigments to capture every last bit of warmth and light. It's a stunning thought. Alien algae blooming across waves under a dim crimson sun, glowing faintly as they turn starlight into chemical energy. Let's speculate further. What forms could life take? Floaters, like Earth's jellyfish or siphonophores. These creatures might drift in the oceans, absorbing nutrients, exchanging gases, and flashing signals to one another in pulses of light. Swarmers, imagine vast clouds of microlife, like alien plankton, moving with the tides and releasing DMS as a metabolic byproduct, just like Earth's phytoplankton. Thermocrawlers, maybe some organisms evolved to cling near deep thermal vents, thriving off chemical gradients, never needing light at all. Balancers, in the dense, pressurized ocean of K2-18b, some life forms might develop gas bladders or hydrogen sacs to hover at specific depths. Too deep and they're crushed. Too shallow and they're starved. Could there be intelligent life? That's a much harder question. Intelligence requires stability, energy surplus, and evolutionary pressure. But simple life, microbes, colonies, primitive hunters, or grazers, that feels possible. There's one huge issue we need to address: pressure. If the ocean is thousands of kilometers deep, then even the shallowest layers might be under dozens or hundreds of Earth atmospheres of pressure. That's enough to crush human submarines like tin cans. But nature finds a way. On Earth, we've discovered life in the Mariana Trench, 11 kilometers deep, under 1,000 times the surface pressure. Microbes, fish, Even shrimp-like amphipods thrive there. Alien life might use flexible structures, amorphous cell walls, or pressure-adapted enzymes to survive conditions that would kill us instantly. That doesn't mean we could visit, but it does mean something could live there. All of this, every speculation, every theory, comes from looking at a few wobbly patterns of light. We can't take a photo of K2-18b's surface. We can't drop a probe. We can't even see the planet directly. Only its star and the way its light flickers as K2-18b passes in front. And yet, from those whispers of photons, we build entire worlds in our minds. Worlds of oceans, clouds, and possibly life. That's the power of astronomy. It makes the invisible feel close. It turns distant suns into destinations. Let's come back to reality. All the excitement about DMS and Hycean life is thrilling. But how do we go from speculation to confirmation? Can we ever really know if there's life on K2-18b? Could we ever send a mission to K2-18b? Let's do the math. Distance, 124 light-years. Current fastest spacecraft, Voyager 1, 17 km/s. Time it would take to get there, 2 million years. Yeah, no? Unless we master breakthrough propulsion, like laser sails, fusion drives, or something out of science fiction, we won't be visiting K2-18b physically anytime soon. So for the foreseeable future, our only way to touch this world is through photons and math. But don't let that discourage you. The reason K2-18b is such a big deal isn't because we've found aliens. We haven't. It's because it represents a paradigm shift. Before now, we focused on planets that looked like Earth. Same size, same distance from a star, same atmosphere. But K2-18b says, what if life doesn't need Earth? What if the universe is more creative than we imagined? What if it has dozens of paths to habitability? Maybe the cosmos isn't filled with Earth clones. Maybe it's filled with Hycean giants, lava worlds, carbon planets, super-Earths, mini-Neptunes. And life finds a foothold wherever it can. K2-18b reminds us that life might not be rare. It might just be strange. And the search for that strangeness, the idea that something alien could be watching that red sun rise over a hydrogen sky, that's what keeps us looking up. If you've made it this far and your curiosity is still alive and kicking, take a moment to hit that subscribe button. We explore the edges of the known universe, one strange world at a time. Don't miss what's next.